Hello, I'm Aaron McIntyre, Building Science Engineer for the Seed Home. We are now nearing the final portion of our tour of our thermal envelope. The roof of the home is not only a primary weather barrier and should be treated as such. Along with the attic, it can be a significant area for energy loss from the home. For proper rain deflection, we need to design clean roof lines with minimal valleys and intersections, and when required, are properly flashed. Roofs should have the adequate eave overhangs on all sides, including gables, all of which are fundamental to deflecting bulk moisture away from the home. With respect to energy, most of the principles we have discussed throughout the tour remain true. Whether we are constructing an insulated rafter assembly, as you see in the dining room area of our attic assembly, we must identify our air barrier and ensure it is well sealed. In the case of our raftered roof, we can think of this no differently from a wall assembly on an angle. It is very critical that this assembly is thoroughly air sealed, as warm air will rise and seek out potential pathways into the rafter assembly. As air moves through the assembly, it will eventually reach a point that the moisture will condense within the roof. To avoid this, first prevent air from moving through the assembly. Then, just as in the wall assembly, layers of extruded foam on the exterior or spray foam within the cavities provide an air seal and a warmer surface within the roof cavity, reducing the potential for condensation. Additionally, allow for an air gap to the exterior of the insulation, which provides a drying path for materials if condensation occurs. Lastly, provide an adequate amount of R value for your region within the assembly to reduce the thermal loss. In regards to attic assemblies, our weather barrier and thermal barrier are separate. The weather barrier is at the roof line, and the thermal barrier is at the ceiling line. Again, we want to air seal the thermal layer as well as possible. This is typically done before insulation is installed by foaming partition wall top plates, electrical boxes, plumbing and electrical penetrations, etc. It is also best to avoid recessed can lighting in the attic. Each light presents a penetration into the attic insulation and is often poorly air sealed. Any potential connection from the conditioned space to the attic space must be well sealed prior to installation. Once this is done, insulation can be added to a recommended level for your climate area. With the insulation space now air sealed, insulation performance will be significantly improved as a result of minimized air movement. An additional feature to consider is the use of raised heel or energy heel trusses. At the perimeter of the attic, the eave area, typically the heel of the truss is only 3 to 4 inches. A raised heel truss increases this distance to 8 to 12 inches. This allows for the proper thickness of insulation at the eaves within the attic, reducing heat loss, which often contributes to ice damming at the eave. One side effect of a well-sealed and well-insulated attic is the increased need for attic venting. To provide for proper moisture removal in the attic, it is critical that the attic ridge venting and soffit venting is provided. This becomes even more important with less heat loss into the attic. Since the air in the attic is now cooler, it has less moisture carrying capacity, which means assuring continuous venting becomes even more important. One last caveat to consider is not to route any ductwork through the attic space. Ductwork in the attic provides for an opportunity to lose conditioned air through leaky ductwork and inadequately insulated ductwork. This is an item that should not be overlooked in design, and whenever possible, chaseways and bulkheads for ductwork should be designed within the thermal envelope to eliminate the need to route ductwork within the attic space.